No, Nicole, I have not said anything yet. We haven't started. We start at 10. Now I'm going to say, okay, welcome everybody to one more week of suffering online. And this homework is going to be due the Monday after the exam. This homework has to do with beams. Beams is not included in this exam. So this homework is due the Monday after the exam. The only thing that is included in the exam is the bonus from exam number one. Well, everything related to weld and columns. So beam are not part of the exam, but this homework is due the Monday after the exam. Okay? All right. Well, I want you to pay attention to what I have to say and what I have to show you. I know that you are worried about the exam and you are stressed out because of too many courses online, because of family problems. So I understand. So I'm going to try to help you. So I want you to pay attention. I know that some of you are still in bed, some of you are still driving, some of you will be here later and asking about this. Look, number one, the exam is going to be open notes, open book, open solution manual, everything is going to be open. However, the exam in number two, don't talk to anybody. Don't help anybody. Help yourself. Right? Because if you do work as a group, somebody gonna tell me, and all of you, the one of the group, is gonna get an F. If somebody asks you a question on the phone, say no. So I'm trusting you. Number two is the most important part of the exam. The exam will start at 7 o'clock. You're gonna download the first question from the folder. Before, please turn that mic off. Turn that mic off. So the first question, I don't know who you are, Amira, I think, turn that mic off. So the first question next week on Tuesday at 7 o'clock in the morning, you're gonna download the first question. But I will also, in this screen, the first question will also appear. So you're gonna have the first question in front of you for an hour if you need it. Also, the chat is going to be on so you can ask me questions, but you're gonna have to turn your mic off during the exam and keep your webcam on so I can see. And some of you, whenever you email me something, I cannot read it. So make sure that you use a very dark pencil or a pen, but it has to be clear so I can read it. But you cannot upload after 8 o'clock, you cannot upload your answer. So make sure that you start at 7, you upload question number 1 at 8. At 8 o'clock, you're gonna download the question number 2, and I will also put question number 2 in the screen. And you have to upload it by 9 o'clock. Otherwise, I'm not gonna grade it. The bonus question is going to be ready by 9 o'clock, so you can download it. I also will put that in the screen. But before 10, you have to upload it. And don't forget, use a very dark pen. The bonus is gonna be also 10 points. So maximum that you can get in this exam, 150 over 100. So the maximum point, 150 over 100. Any question before I continue with the lecture? Okay, I will put these instructions also in Blackboard. I will send this to you probably tonight. Will there be a review? Stella, we already had talked about the review. The review starts tomorrow. Today, I'm gonna try to finish the beams and we'll continue probably a little bit tomorrow, but tomorrow we're gonna have the review. Next Monday, we're gonna have also more review and also a question and answer section. If you don't have a webcam, don't, I understand. Don't buy one. Don't buy one. Just tell me you don't have a webcam. I trust everybody. If you finish the question before time, congratulations. You are good. Any other questions? Okay. If you finish the question before time, keep reading, prepare yourself, relax, be ready for the second question. Okay. In chapter G in the code, they had all the equations that had to do with the design strength for beams based on the shear forces. In the old times, this chapter was part of chapter F. So in the last code, it had its own chapter, chapter E. What I want you to understand is that for a wide flange beam, and you remember this from mechanical solid, this is the shearing stress distribution. The shearing stress distribution, as you know, is always different depending on the cross section. It has a different shape. The cross section they use the most for beams is a wide flange. If you remember from mechanical solid, it's zero in the outside, maximum at the neutral axis. But most of the shear stresses are resisted by the web. So the code assumes that the web, all the web, the depth times the thickness of the web is resisting the shearing stresses. So the code assumes that this is a rectangular shape because most, as you can see, most of the shearing stresses are resisted by the web. The code assumes that the web is resisting all the shearing stresses. So I want you to go to chapter G on page 16.17. Chapter G 16.17. For shear, you have to be very careful because they tell you that for RFD, you have to use zero 0.9 with the section of this section that is in the next page. And the shear strength equation, this is a nominal strength, is 0.6 F1. This is the area of the depth and the thickness of the web. I'm going to solve the problem related to this. On the next page, and you have to be very careful because it's for eye-shaped members. And this is H over TW. Whenever this is smaller than this value, phi is 1. Phi is 1 instead of 0.9. And the shear factor is 1. And there are other conditions. If you look at this value here, there are conditions where the value of C sub B1 is computed, like given here. We're going to do that later. What is important to know is that the code assumes that all the shear stresses are resisted by the area of the web. Another thing that is important to know, whenever we have beams, and look, you cop, this is COP, you cop the beam to be at the same floor. You're going to have it here, the flange of a girder. So to be at the same level, you need to cop the beam. So in this case, there is a shear block. This is the gross area in shear, the net area in shear, and this is the gross area in tension and net area in tension. And in here, you can see that this is the same block shear equation that we used before, the same definition for the gross area, for the net area. This is important. This value of U still is 1 for most of the cases. However, based on research, is 0.5 when we had 2 lines of bolts. So this is 1 line of bolt. Whenever we had 2 lines of bolt, it would be 0.5. I want you to remember that. And the last piece of information I want to give you is about the flexure. Whenever we do beams, we have to check the strength based on moment, sigma is equal to MC over I. The strength based on shear, we look at the shear stress, tau BQ over IT, and deflection. Deflection is based on service load. Deflection, we do not factor the load. So deflection or LRFD, ASD, always based on service load. We do not factor the load. In addition, normally the dead load deflection, whenever you load the structure during construction, is already taken care, already taken place. So the only thing that we consider is the live load deflection. And you can see that the textbook says the same. So all that we're going to be looking at is L over 360, L over 240. So typical for floor beams, L over 360 and L over 240. But this is just based on live load. And I will tell you, use L over 360 or L over 240. This will be given to you. They have to be in inches. So the span has to be multiplied times 12. But only uses the live load. And this is a typical formula. You can find this at the end of chapter 3, typical deflection formula, always in inches. So today we're going to do our first design. And like I mentioned to you last week, we're going to be looking at chapter F that deals with bending or flexure. Chapter B that had a table for H over TW and B over 2 times the thickness of the flange for local buckling. And in chapter 3, we saw the other day that we had a table for ZX plastic modulus, IX model elasticity about the strong axis, ZY and IY. Later, after our exam, we're going to be looking at the different type of beams. Also, we're going to be using chapter 3, a table. Something that I want to point out in chapter 3. I mentioned to you before, but now I'm going to show you where to find. Go to chapter 3, page 5. Chapter 3, page 5. This is what I showed to you before. This is horizontal, this portion is linear, after that comes a parabola. So this is when we develop the plastic moment, and in the code in chapter F, they call it yielding. And this is when we had P M sub N is equal to Phi M sub P. And this point, if you go down below, this point corresponds to L sub P. So all the problems that we're going to solve today, all the problems that we're going to do related to beams, they have this condition. They call it fully supported compression flange. So the compression flange is not going to back up. We are not going to have what is called lateral torsional buckling, or LTB. It's not going to happen in the chapter. So everything is going to be in here. If you look at this value in here, this is whenever we have problems with the flange or the web. We're going to also look at this. But right now, everything is going to be fully supported. The compression flange. Our first problem. This is page 23 of our notes. Here on the top, it says continuous lateral support. That means that the compression flange is not going to have lateral torsional buckling. This is what I told you before, that the compression flange could be encased in concrete. That calls, or they call it continuous lateral support. We still haven't here the support. The beam still is determinant. We had a pin and a roller. What they're saying is that the compression flange is encased in concrete. The dead load 450 pounds per foot, and the weight of the beam is not included. The live load is 550 pounds per foot. And when you look at this, W16 by 31, that means 31 pounds per foot. So the load that we had is 450 dead. I need to include to this dead 31 pounds per foot. So down below here, I have computed WCU. The dead load per foot in kips. This is the weight of the beam. This is 31 pounds per foot. Divided by 1,000 to kips. So this is in here 31 pounds per foot divided by 1,000. That gives me the 31. Given that load plus the weight of the beam times 1.2, the live load times 1.6, this gives me 1.457 kip per foot. So this is the load that we have in here, 1.457 kip per foot. If you multiply this times 30 and divide by 2, give you this reaction that this is this value, 21.8 kips. So 1.457 times 30 divided by 2 gives you the reaction. This is the reaction. The moment, the maximum moment is W to U L squared over 8. It's 1.458 times 30 squared over 8, 163.91. So we have to provide a moment capacity larger than 163.91. So we need to check. They want to know, is this section, the W16 by 31, can resist 163.91 kip per foot. Since this is fully supported, the compression flange is fully supported in chapter F. they say that the limit state that applies is yielding. So I want you to go to chapter F and in page 16.147. 16.147 in this page, it says that the limit state yielding, this is when wherever we have the compression flange fully supported or the bracing of the compression flange is equal or smaller than L sub P. In this case, the limit state yielding says that the nominal, this is the nominal capacity for both LRFD and ASD. So the moment that we're going to develop is the plastic moment, fully yielding of the cross section. The shape of the stress diagram on the cross section, rectangular. So for LRFD, phi m sub n is equal to phi m sub p equal to phi my cf. In addition, we need to go to chapter B. This is the table in chapter B on page 16.1. This is the table that is for beams. Don't get confused with the previous page table that is for columns. So make sure that you understand there are two tables, one for columns, one for beams. Beams, we call it Flexure. So in order to the section that we are dealing with in order to develop the plastic hinge, local buckling should not take place. That's why we have to check B over 2 times the thickness of the flange. Why is B over 2? Because look at this. This is what is B in this equation. So B over 2 times the thickness of the flange has to be smaller than lambda sub P. And this is given in chapter 1, this value. For the flanges, on the next page, for the web, on the next page, for the web, we had H over TW. H over TW is smaller than this value. So this is also given in chapter 1. So from chapter 1, chapter 1, we already done it before. B over 2 times the thickness of the flange for the W16 by 31 is given as 6.28. This is our value of lambda. Has to be smaller than 0.38 times the square root of 29,000 over 50 because FY50, 9.15, 6.28 smaller and equal to 9.15. No problem with the flow. The web, H over TW, this value comes from chapter 1. For W16 by 31 had to be smaller or equal to 3.78, root of 29,050, 91.03, smaller, no problem. So the section is compact. This value Cx comes also from chapter 1 or from chapter 3. This is the plastic modulus of this section, 16 by 31. So this comes from chapter 1, whenever we had a 16 by 31, or come from chapter 3. I'm going to show you later how to use chapter 3. Since we have full support of the compression flange, no lateral torsional buckling will happen. We do not have local buckling of either the flange or the web. Yielding is the limit state this is what I show you. Phi M2N equal to phi M sub P, phi FYZX. And this is the equation in chapter F, F2-1. The value of phi 0.9, the value of y 50, zx 54 inches to a third. You have to divide this by 12. That gives you 202.50 kip foot, larger than the one that we obtained when we found M to U. So this value in here is M to U, that was WL squared over 8. So the conclusion is that the section is added. Any questions about this problem? It cannot be that clear. Any question? I think that you all went to sleep. I'm going to go to the next problem. This is page 25. Example 2, they give you the W10 by 77. This weighs 77 pounds per foot, and there is continuous lateral support. In this chapter of the textbook, everything has continuous lateral support or is braced, compression flange braced at a unbraced length L sub B is smaller or equal to L sub B. And you can see this in the field. I don't know if you were able to go to the field or not, but this is very simple. You can see it in it. So they want to know what is the maximum point load, live load that can be applied to this beam. And this beam in here, it has the load and mid-span. I have factored the live load 1.6. The only dead load that we had is the weight of the beam. So you can see in here that I had divided the 77 pounds per foot by 1,000. So I have in here 0.077 kips per foot times 1.2. So the load, the dead load is 0.0924 kips per foot. So we have factor the dead load, we have factor the live load, and this is our problem. I had broken this into two diagrams to add the moment produced by the point load to the moment produced by the uniform load. You have to be good at structural analysis because if the load is not in the center, you have to find the location in the shear diagram when the shear is equal to 0, because when the shear is equal to 0, the moment is going to be maximum. And here, because of symmetry, the moment is going to be maximum at the center of the span. So 1.6 is this load divided by 2 times 15. So in this diagram, (1.6) P divided by 2 is this reaction. Multiply times 15 feet. This moment in here, in terms of P, is 12 P. The moment produced by the uniform load is still W to U times L squared over 8, 10 points. So the moment that I had to design for is 12P plus 10.40 kip per foot. This is just a structural analysis, and I know that you're very good at this. So what we had to do, we had to equal the moment capacity of the W10 by 77 to the required moment that is 12P plus 10.4. And this is what I had done in the next page. Show calculation, can we use table 323? Right now, I want you to use calculation. it's good for you to understand how to do the calculation. I always want you to do calculation. Whenever I tell you don't use calculation, use a table, I will point that. But that I'm glad you asked that. Okay. So look, chapter 1, W10 by 77, B over 2 times the thickness of the flange is smaller than this value, no problem with the flange. H over 2W, 14.8 is smaller than 91.3, no problem with it. ZX, it comes from chapter 1 or chapter 3. And this is the equation. We do not have problems with the flange, no problem with the web. And fully support the compression flange means no lateral torsion buckling. Yielding is our limit state, the same as before. The nominal strength equal to the plastic strength, PFYCX. The CF came also from chapter 1, or it could come from chapter 3, from the table 323. I'm going to show you that much later. So we have 0.9 times FYZX divided by 12. Don't forget to divide it by 12. 366 keep foot. We're going to make this equal to the required moment. And from here, it came 29.63. Now, we're going to go to table 323. Chapter 3, page 223. This is the table for GX that I mentioned last week. In this table for GX is only for 50 KSI. For yielding, the equation that we're using is a linear equation because phi m sub n equal to phi m sub p. P is a constant, Fy is a constant, Gx has nothing to do with the type of steel. Gx is property of the geometry. So the only thing that we need to do to the value here for P m sub phi for any type of steel, you divide it by 50 multiplied by the Fy required. But in this table, the Zx, this is the Zx table because the Zx is given. And also the phi m sub p, phi m sub r, we had the value of L sub p, L sub r, and I sub x. In addition, it gave you the shear capacity, shear strength of this section. So look for the W10 by 77 in here. On page 3-25, go to page 3-25. We always do keep foot. Somebody, I think Fernando Rodriguez, he answering the question. Yeah, because look, let me finish with this. I'm gonna go back to show you the unit. At the bottom of this page, we had a W10 by 77. What is the value? Anybody type, what is the value of P M sub P that we had in here? For 366. And what is the value that we computed? Look. Exactly the same value. So we're going to use this table, but right now I want you to know where this value is. There is a question about the units. Look, 50 is kept inch square. This is inches to the third. So 50 keep inches square, this is inches to the third. So when we multiply this, what are the units? If I multiply this times this, what are the units that remain? What do I have? Keep what? If I multiply this times this, the units I keep what right now? Before I divide by 12, keep inch. So we need to divide by 12 to have keep foot, because everything is given a keep foot. Any other question about this problem? Or any problem? So I'm going to go to the next one that is a little bit more difficult. This is page 27. Page 27, they give you the dead load that says the weight of the beam is included. 1 kg per foot, the weight of the beam is in. The live load is 2 kg. For the first time, we're going to check deflection. And the maximum deflection produced by the live load, service load, and factor load. Service load, live load is L over 360. A point load, then load 40 kg. So what I had done in here, I have factor 1.2 times 1, 1.6 times 2. That gave me a factor load 4.4 kg per foot. The 40 kg in here, the 40 kg is a dead load, it's not a live load. Times 1.2 give me 48. So this is the problem that we have right now. And this is just a structural analysis. We have already factored the load, the point load, the uniform distributed load, but the load is no longer, this is no longer at the center. Condition of this problem, continuous lateral support. So you have to be careful, continuous lateral support. And I had done in here, I have computed the reaction. This is 118, this is 106. This reaction, it doesn't say in the problem that the beam weight is included already. We had to add, yeah, of course. And I'm going to solve some problem later that the weight of the beam is not included because we do not have any idea the size of the beam. So we have to, we have to revise our moment. At the end, the MU that we computed for the problem that Nicole is asking, the MU had to be revised. So we had the old MU, we have to add 1.2 times the weight of the beam, in this case, L squared over A, or whatever location the maximum moment is. And that's a good question. So I had computed the reaction on the left, 118, and on the right, 106. And this value in here, where the point load is, I had done the shear 118, I had subtracted this 4.4 times 15. So 118 minus 4.4 times 15 give me 52. And 52 minus 48 give me 4. After that, I had 25 times 4.4 give me 106. and this close it back to 0. I need to find the point where the shear is equal to 0 because the moment is going to be maximum at this location. And I did it by similar triangle, so I found that it was 0.909, 2409. So I found the maximum moment when the shear is equal to 0 is 1276.80. Here at the bottom, I'm finding the maximum deflection L over 360, the span is 40. You can see in here the span is 40 feet. 40 times 12 divided by 60, the maximum deflection in inches, 1.33. Sometimes I'm going to compute the maximum deflection first. Sometimes I'm going to do it after I check the section. I'm going to check the section. Look, in this problem, the section is not given. The previous two problems, the section was given. And here we're looking for the section. So at this time, I don't know what is going to be the lightest section. So we assume that it's compact. That means they're going to be able to develop the plastic hinge. If it's compact, phi m to n is equal to phi m to p, phi f y cx. This is the equation in chapter F, the yielding equation. Limit state the whole cross section is going to reach Fy. It's going to develop the plastic hinge. The stress distribution on the cross section, rectangular. On the tension side, rectangular. On the compression side. So phi m to n, the design strength, larger or equal to the required m to u. 0.9 times 50 Fy. Zx is unknown. I have to divide by 12 to have keep foot because my moment, this moment comes from the previous page. This moment is the maximum from the previous page in keep foot. So I was saying phi m to n equal to phi m to p. 0.9, 50 Zx divided by 12 equal to the required moment. This moment is in keep foot. So Zx required, look, for the first time, I'm calling this Zx required 340.49. Now we have to go to the table for Zx in chapter 3 on page 323. So we had no choice but to go to the table for Zx in page 323. And we had to look. I mentioned to you the other day, I'm going to mention again. There are groups. The one on the top of each group, the one that is dark, real dark, is the lightest, the best section of this group. You can see 146, 252, 166, 233, 132, 192, lightest ones at the top. So we go and we looking for 340, for ZX 340. Look in this group. and somebody already gave me the answer. Look, we're looking for 340 or more. This one, the W27 by 142 by 114, W27 by 114, has 343. That's what we need. However, this is the lightest one of the group. It gave me more with less weight. So this is the second, like Hugo had put in here, a W30 by 108. And that gave me a 346. It gave me a moment inertia. If you look in the same page, I sub X for the W30 by 108. What is the value of I sub X? Somebody write it. 44 seconds. So W30 by 48, 346, 346, and 44 seconds. So with this required value, we went to table GX. We found that the W30 by 108 is the best, the lightest one. It gave me a ZX of 346. It gave me a moment inertia about the strong axis 4470 inches to the. Of course, I had to check the flange, the web, 689 is smaller than 915, no problem. 49.6 is smaller than 91.3, no problem. For the deflection, you go to chapter 3, page 3, 2008. That's at the end of the chapter. At the end of chapter 3. Whenever we're doing this, I'm going to tell you, go to the end of chapter 3. Page 3, 208. In the future, most of you are going to become what we call table engineer. Everything you're going to go to the table. Hopefully you will remember where everything is. Why I'm using this case and why I'm ignoring the point load? If you look at this problem, this is the problem that we're dealing. Why I'm considering this, I'm not considering the point load. Anybody? Live load only, good. Live load only, and here, look, this is the live load only. We consider the deflection produced by the live load because the deflection produced by the dead load already taking place during construction. Already happened. The one that we are concerned with the structure is in service. So we only consider the live load. That's why I went to this case. And in here, he said that the maximum deflection happened at the center, IW4 with 384 EI, and this is what I got in here. This is the deflection formula, 5W squared over 384 EI. This is the maximum deflection L over 360 that I computed before, 8 inches. I is a constant. Look, if you look at the 40, What is this 40 in here? What is this 40 in here? What is this 40 in here? To the 4. Anyway, what is the 40 here? No. Look at the formula. The W is here. What is this W? What is this? Look, the W, what is this 2 here? This is the live load and factor, service load, keep put. This is the span, like you said, the span is 40 to the 4. But I need to multiply only times 12 cubed because this 2 is already in keep per foot. So this is already in keep per foot. So I only need to multiply times 12 cubed. 384 is a constant. EO is 29,000. We call what is the required value to produce 1.33. It came at 2986.78, smaller than 44.70, so it's okay. So W30 by 108 is the best section. Yes, I'm going to put in W again. When we started the problem, look, live load, service load, 2 keep per foot, and factor load. The deflection, consider only the service load, only the live load. So this 2 keep per foot is unfactored live load. When I come to this formula, the deflection is a service condition. It's a called serviceability or performance. In today's language, it's a performance of the structure. This is L over 360. This is the live load, the 2 kg per foot. This is the span to the 4. And this is 12 cube because this is already keep foot. So it came the required 2986.78 is more than provided. The section is okay. Any other question? Because I need to tell you something else before. If and only if this is larger than the provided, if the required moment inertia is larger than the provided, we have to go to table on page 328, 329. Look, chapter 3, page 329. Chapter 3, page 29, page 28. This is the table for the moment inertia about the strong axis. Why doesn't say here Fy equal to 50? Why it doesn't say in this table? Anybody answer? Why it doesn't say for Fy equal to 50? This value Ix. Based on the geometry, nothing to do with it. But this table, whenever you have a problem with the deflection, that you need to have more moment inertia, you go to this table with the required moment inertia. The one on the top is the lightest section that will provide what you need. We're going to solve problems like that. I need to stop in here. I'm sorry it took 5 more minutes. Any question before we go? Tomorrow, I'm going to do the review for the exam. Any question? Okay, so tomorrow, make sure that you are on time. We're going to do the review for the exam. And we will continue reviewing next week on Monday. Okay, no more questions. So I'm going to turn everything off. See you tomorrow. at the review. Bye.